Hey guys, welcome to lesson 8.3, adding and subtracting rational expressions. So recall, we just finished up multiplying and dividing rational expressions. And now we're going to look at adding and subtracting rational expressions. Now usually, like when we first start learning operations with real numbers, way back in, probably preschool even, we usually learn about adding and subtracting first, and then multiplying and dividing. But so why do you think it is that we started off with multiplying and dividing with rational expressions? Well, when you think about fractions, it was always easier to multiply and divide fractions because to multiply and divide fractions, you don't have to have what's called a common denominator. And that is what makes adding and subtracting fractions more difficult. And that's why we're looking at adding and subtracting rational expressions after we've looked at multiplying and dividing. It's a little trickier, but I'm sure you can handle it. So we have these three learning goals. Our learning goals are to add and subtract rational expressions. We're going to add, subtract rational expressions with and without common denominators. So sometimes we'll be given ones with common denominators, and that'll be pretty easy, and some without common denominators, and we'll have to do a little more work there. Secondly, we're going to find the least common multiple of a pair of polynomials. So we'll be looking for an LCM, least common multiple. And finally, we'll be simplifying complex fractions. Well, I already think these look pretty complex, so they're going to be even more complex, and we're going to simplify them. So as I mentioned in the opening, adding and subtracting rational expressions is similar to adding and subtracting fractions. And when we think about how we add and subtract fractions, we again think right away of this whole idea of a common denominator. So if I asked you to add 1/6 and 1/3, if I asked you to multiply them, that'd be easy. You just multiply the numerator and the denominators. But if I asked you to add them, now we have a little work to do before we can actually do this addition. We have to get what's called this common denominator. So what we do is we look for the smallest number that 6 and 3 will divide in evenly. And we actually call that the least common multiple of the denominators. So that we want to find the smallest number that these two divide into, because we don't want to get any bigger denominator than we need to. We want to get it as small as possible, but yet works so that both denominators divide into it evenly. And so right away when I think about 6 and 3, like the tendency might be to think 18, because 6 times 3 is 18, but there's a smaller number that they both go into. They both go into 6. So actually, if I chose 6, I wouldn't even have to change the denominator on 1/6. And so that's actually what I'm going to do. It's the smallest number that they both go into is 6. So I want to change the denominator of 1/3 to 6. And the way that I'll have to do that is multiplying that denominator by 2. That'll make it 6. But if I do that, I also have to multiply the numerator by 2. Because then in essence, I'm really just multiplying it by 1, because 2 over 2 is 1. So I'm not really changing it, I'm just changing what its denominator is. So then that changes this problem to 1/6 plus 2/6, because now 1/3 with a denominator of 6 is 2/3. Now I can add the numerator, so I add these two together. But the denominator, remember, does not change. I mean, we do add the numerators together, and that will give us 3, but the denominator stays 6. It's always the same as the common denominator. So 3/6 would be my answer, which then, of course, could reduce to 1/2. So we'd want to make sure we reduced it to 1/2. So that process that we're going to use is very similar to just with basic numeric fractions. And that is, if the denominators are already the same, you just add the numerator, and the denominator will be the denominator of the two terms that you are adding. If it's not a common denominator, then you have to get one. So let's take a look at example 1, which is adding and subtracting rationals with like denominators. So these already have the same denominator or common denominator. So if we take a look at example A, we want to add x minus 3 over x plus 4 and x minus 2 over x plus 4. So again, they both have the same denominator. So that means the denominator of my answer is going to be x plus 4. And to get my numerator, I'm simply going to add my like terms together. I'm going to add the two x's together. X and x is 2x, and minus 3 and minus 2, they add to minus 5. So my answer, or my sum, is 2x minus 5 over x plus 4. Now again, in this situation, we want to make sure we clarify which values the x cannot have, and so we know that a negative 4 would make the denominator equal to 0, so we want to make sure we exclude that. Now, it always is a good idea, too, to look at your final answer, this 2x minus 5 over x plus 4, and see if there's anything you can do to reduce it any further. There's not in this case, but that's a step you want to make sure you don't neglect. So, if there was a way that you could break those down further and cancel anything out, you want to make sure you do that. So let's take a look at example B. So I noticed that I have a common denominator of x squared plus 1. So I'm going to go ahead and write that as my denominator, and I'm going to, this time it's subtraction. Ooh, I almost missed that. So this one is subtracting. So I have to subtract my like terms. So I've got a 3x and I'm subtracting 6x. So 3x minus 6x is a negative 3x. And then I have a negative 4 and I'm going to subtract a positive 1. So negative 4 minus 1, that's negative 5. Now, I think about whether there's any way I can break down the numerator and the denominator. And really, I mean, the numerator, the only thing I could do is maybe divide out that negative or factor out the negative. But the denominator, x squared plus 1, that's a sum of squares, and that's not factorable. So there's really nothing I can do to break that down. So that is my final answer. And the only thing I really need to do now is to tell what value the denominator can't have. So if I think about that, x squared plus 1 equals 0. And I want to know where this is undefined for the real numbers. Well, if you think about, there's really nothing that you could put in for x that would make this equal to 0, because there's nothing you could, no number you could square and get negative 1, which is what it would take to make that 0. If you were to subtract 1 from both sides and you had x squared equals negative 1, see, if I take the square root, that's plus or minus I, but we want to know over the real numbers. So this is actually defined. It's actually defined for all real numbers. So that's the key, real numbers. There are some imaginary numbers for which this would be undefined, but we're just focusing on what real numbers would make this undefined, and there are none. So let's go ahead and make C a U-try question. And this one is an addition, so this one should be similar to example A. So go ahead and pause the video now and add the fractions in example C. All right, so thanks for trying that example. Check your answer, and if for some reason you didn't get 9x plus 4 over x squared minus 3, and you didn't identify plus and minus the square root of 3 as the places where the function or the expression would be undefined, then maybe pause the video, take a look at the work, see if you can figure it out, and if you still can't, then make a note and be sure to bring that up when we see each other in class. Let's go ahead and turn the page. Okay, so since we can only add and subtract rationals with like or common denominators, we need to find and use the least common multiple so that we can make the denominators be the same. So we're going to force them to be the same by identifying the least common multiple of the denominators. So again, we use the least common multiple, or the LCM, to get common denominators. So example 2 asks us to find the least common multiple of some polynomials. So let's take a look at example A. So those are both monomials, just single term polynomials. And so if we wanted to find the least common multiple, well, because it's got variables and it's got numbers and everything, we're going to kind of look at it in pieces. Let's take a look at the two real numbers, the coefficients, the 4 and the 6. If I wanted to find the smallest number that 4 and 6 divide into, and I think about, the multiples of 4 and the multiples of 6. The first one I come to that's common is 12. So I know the least common multiple of 4 and 6 is 12. Now when I look at the x squared and the x to the 4th, the number on the exponent, on the first one, x squared, and the second one is x to the fourth. If I wanted to be able to divide this least common multiple by both x squared and x to the fourth, I'd have to be able to have the one with the highest power to be able to divide into, which means that when you have variables, you always want to take the highest power as the least common multiple. So we'd make that x to the fourth power. So with that same thing in mind with y to the third and y to the fifth, the least common multiple would be y to the fifth. Now the reason why that is when we divide with variables, with exponents, we actually subtract the exponents. So you could divide in y to the third into y to the fifth, and you'd get y squared. So it is, y to the fifth actually is a multiple of y to the third. It's actually y to the third times y squared. And so if we put all these things together, that right there is our least common multiple. It's 12, x to the fourth, y to the fifth. So in general, for the variables, you take the highest of the powers that are represented. So keeping that in mind, you try example C, because that one is very similar to example A. So go ahead and pause the video now and find the least common multiple of example C. Okay, that's 12, x to the fifth, y to the seventh. We took the least common multiple of 4 and 3, which is 12, and then the higher of the two powers on the x's and the higher of the two powers on the y's. Okay, what about if we have, like, say, trinomials or binomials? Then what do we do to find least common multiple? Well, it turns out to find the least common multiple of binomials, trinomials, more term polynomials, the first step would be to factor them. So, and then to see, what do they have in common? Do they already have some common factors in them? And the only way we know that is actually by factoring them. So let's take a look at our first polynomial, x squared minus 2x minus 3. So if I were to factor that into two binomials, the reverse FOIL, they'd both start off with x. I have to multiply two numbers that are going to go in these other two spots and get negative 3 and add them to get negative 2. So that's obviously going to be minus 3 and positive 1. Now I'm going to go over here and look at x squared minus x minus 6. Break that down. So the two binomial factors will be x, both start with x, and they'll end with factors of negative 6 that add to negative 1. So I thought right away of negative 3 and positive 2. Negative 3 times positive 2 is negative 6, and negative 3 plus positive 2 is negative 1, which is that middle term. And so now if you take a look, these two polynomials actually had something in common. They both had an x minus 3. So I know that's actually going to be part of the least common multiple. It's going to be x minus 3, but then this one over here, the one on the left, actually has an x plus 1, and the other one doesn't have an x plus 1. So this one on the right would actually need an x plus 1, and the one on the left would need an x plus 2 because it doesn't have that factor that the other one has. And so essentially what we do is once we factor it, we just list all of the binomial factors. And we don't put any repeats because if there was repeats, then that means it was a common factor of both already. So our least common multiple of these two polynomials would be x minus 3, x plus 1, and x plus 2. So we make sure each one of these binomials is represented, and that would give us our least common multiple. So why don't you give that one a try in example D. You try question. Pause the video now and see if you can find the least common multiple of those two polynomials. So our least common multiple, x plus 2 times x minus 2 times x plus 3. Okay, so now that we know how to find a least common multiple, which really is what we mean when we say common denominator, let's go ahead and see if we can add fractions that don't have a common denominator. So example 3 asks us to add rational expressions. And so our two-step actually the directions are flip-flopped. It should say 1, identify any x values for which the expression is undefined, and then 2, add. So they want us to do these two things. So that's step 2 we want to do first. We want to look and see what would make any of these denominators undefined. And so if we take a look at, to do that, we have to look at the denominators and factor them. And we really want to factor them anyway because we're going to try to find the least common multiple. So when I first look, I look at this first x minus 3 divided by x squared plus 3x minus 4. I'm going to go ahead and factor that. And it will factor to x plus 4, x minus 1. That way, they'll multiply to give me negative 4 and add to give me positive 3. And now if you look at the other denominator, it was x plus 4. So if you look at, there's really a common one in both. There's an x plus 4 and an x plus 4. And so I know that since there's an x plus 4 in the denominator, that one of the places where this is undefined will be where x equals negative 4, because negative 4 would make that x plus 4 equal to 0. Now the other place would be the one that's not in the second fraction. It's the x minus 1. And so positive 1 would make that equal to 0. So I've identified my places where this is undefined. I got that part done. But now I have to think about, well, I want a common denominator so that I can add these together. And so I notice that this one has the x minus 1 and the other one doesn't. So I'm going to go ahead and give this one an x minus 1. But if I multiply that denominator by x minus 1, well, then I have to do that same thing to the top. Remember, I have to keep it in balance. So if I do it to the top, I have to do it to the bottom and vice versa. So let's see if I rewrote those. That first fraction is going to stay just the same. I didn't change the denominator there. It's still x minus 3, and it's over x plus 4, x minus 1. And now I'm going to add to it what I get here. Well, I want to go ahead and distribute this first to make sure I know exactly what that numerator is. It's going to be 2x squared minus 2x, and then over the common denominator of x plus 4 and x minus 1. And now I can go ahead and add the numerators together. So my denominator I know is going to be x plus 4, it's the common denominator, and x minus 1. And now my numerator is going to come from adding my like terms. Well, let's see. There's only just one x squared term. It's 2x squared. So I got that taken care of. That's done. And now I've got an x and a minus 2x. Those put together, if I put these two together, x and negative 2x, they make negative x. And then if I put the constant terms together, the negative 3, and there's not one in the second part, so it's just minus 3. And there is the sum of those two fractions. Let's go ahead and turn the page. All right, example B. First step 1, factor everything. We notice we have two fractions. They do not have a common denominator. I got to get them so they have a common denominator. And so to do that, I'm going to have to see what the factors are. So I'm going to go ahead and take this. The only thing it looks like I can factor at all is the x squared minus 4. That's a difference of squares. And that means I'm going to have two binomials that have identical terms of x and 2 in them, but one of them is going to be a plus and one of them is going to be a minus. So they're nearly identical, but because of the different sign, there would be no middle term when we use FOIL. And so now I can see that what this fraction over here is lacking is it does not have an x minus 2 that the other one does have. The other one, they both have an x plus 2 in the denominator, but this one doesn't have an x minus 2. So I'm going to go over here and I'm going to multiply by an x minus 2. But if I do that, I have to do that to the top. Remember, that's important. If you do it to the top, you got to do it to the bottom and vice versa. And so now I'm going to go ahead and I'm going to look at what that new numerator is going to be when I take that x and I distribute it through. I have to distribute that x to both parts, and that makes it x squared minus 2x. And that's over x minus 2, x plus 2. And then the other fraction is negative 8, and it's over the same denominator, x minus 2, x plus 2. Well, I'm going to go ahead and take care of right away these two places where this is going to be undefined. It's going to be undefined where both of these denominators, these factors in the denominators would be 0, and that would be at 2 and negative 2. So I'm just going to go ahead and take care of that, and now I'm going to do the addition. So when I add these together, there are no like terms to put together on the numerator, right? So it's basically this right here is the numerator. It's x squared minus 2x minus 8, and my denominator is x minus 2 and x plus 2. Now, it's worth taking a look at to see if possible there's a way to reduce this, because it looks like maybe x squared minus 2x minus 8 might be factorable. So I'm going to go ahead and take a look at it. Let's see if we were to factor that. So I'm going to just sort of see if I can go down here and factor that a little bit further. So if I take the x squared minus 2x minus 8, I'm going to break it down into two binomials or reverse FOIL. They're both going to start off with x, and I'm looking for two numbers that multiply to give me negative 8 but add to give me negative 2. And right away, I'm thinking of a negative 4 and a positive 2. Negative 4 times 2 is negative 8, and negative 4 plus 2 is negative 2, so this would be the factored form. And now you can see, actually, that there is a common factor in the numerator and the denominator. Both the numerator and denominator have an x plus 2. So you can just go ahead and cancel out those. And that leaves me with just x minus 4 over x minus 2. And that's my final reduced fraction. Now, what we just did, that very final step, would be just like, say, if we had an answer of like 3/6, and we would reduce it down to 1/2. It's equivalent to this x minus 4 times x plus 2, and then x minus 2 times x plus 2 on the bottom, but it's in its simplest form when we cancel out any common factors. So that's always something to keep in mind, and just do a quick check on before you give your final answer. And because of the nature of the difficulty of some of these kind of problems where we've got to get a common denominator and all that, we're going to leave example C as one to do in class. And that way it gives us an opportunity to open with this when we meet again in class. And that way, we'll have an opportunity to kind of, see if we have any issues that we need to discuss further by going through this example. But there are more problems, so let's go ahead and turn the page. We're going to go ahead and try a subtracting one together, and we'll leave the second one to do in class as well. That gives us an addition one without a common denominator and a subtraction one that we can do when we see each other in class. But let's go ahead and look at example A, subtracting rational expressions. So we see clearly that we do not have common denominators. So let's go ahead and start off by factoring. We want to factor completely. And actually, when we say factor, it's probably best really not to factor numerators right now, because if you get them factored, then you don't have separate terms that you can add or subtract together. So really when we factor, we really want to just factor the denominators. So let's take a look at this x squared minus 9. That's a difference of squares. So I know that that can be broken down with nearly identical binomials. One will be x plus 3 and one will be x minus 3, x plus 3, x minus 3. And so when we take a look at the other fraction, we can see the other fraction has an x plus 3. They both have an x plus 3. But this one's missing that x minus 3. So we want to make sure it gets the x minus 3 also. But to do that, we have to multiply the numerator by that as well, which is going to require us to FOIL that numerator. So when we multiply with FOIL, let's see what that looks like. So we have our first, our outsides, our insides, our last. Our first two are going to give me x squared. Our outside 2 minus 3x, our inside 2, 5x, our last, negative 15. And now when we put our like terms together, we're going to have x squared plus 2x minus 15. Now let's go ahead and rewrite our separate terms. We have 2x squared minus 30. We have a denominator of x minus 3, x plus 3. We are subtracting from that x squared plus 2x minus 15. And again, we have the same denominator. So x minus 3 x plus 3. So now we're to the point where we just have to put our like terms together by subtracting. And again, remember, this is a subtraction, so we're subtracting like terms. It's probably a good time, too, to take a look at the denominator and see that x's value cannot be 3 or negative 3. Those values make the denominator equal to 0. So now I put my like terms together by subtracting. So I'm going to take a look at the x squareds first. So if I take 2x squared and I subtract x squared, I'm just left with x squared. So those are done. I'm going to go ahead and cross those off. Probably a good strategy to kind of keep things organized. Now when I look for another x term, there's not another x term. There's just this one here. Okay? And it says it's a positive 2x, but remember there's this negative out in front. So it's actually saying I'm subtracting 2x, and that makes it a negative 2x. Then we have this negative 30, and we're subtracting negative 15. Well, if you're subtracting a negative, minus negative makes it a plus. So I really have negative 30, and I am adding 15, which makes negative 15. So now I got my numerator all in place. My denominator is x minus 3, x plus 3. And again, it's not a bad idea to think about whether I can reduce this. So I want to take that numerator and see if I can factor it. So I'm going to take that and rewrite it in factored form, if it's possible, and I think it is. I'm looking for factors of negative 15 that multiply to negative 15 that add to negative 2, and right away I think of negative 5 and positive 3. That works. And now I can see that my numerator and denominator have a common factor of x plus 3. So I can go ahead and cancel those out, and all I'm left with is that x minus 5, x minus 3. And that's my final answer in its simplest form. So as I said before, we're going to leave subtracting example B for us to do together in class. Let's go ahead and take a look at our last learning goal. So our last learning goal is to simplify complex fractions. So exactly what is a complex fraction? Well, you'll see a few of them here, and you'll see why we call them complex fractions. Those look pretty complex to me. But a complex fraction contains one or more fractions in its numerator, its denominator, or both. So we could have a fraction that has a fraction in the numerator and a fraction in the denominator. So we actually have a fraction that's divided by a fraction, which we actually have done that. We did that in the prior lesson. We divided fractional rational expressions, or rational expressions, by rational expressions. So this is really something we've already done. It looks a little scarier in the form that we see it in these examples, but I'll show you that it's really something that we've already done. We'll just put a little twist on it. So let's see, this fraction bar right here means the same thing as division, right? That just means divided by. So if we were to take example A and rewrite it with, instead of the fraction bar, instead we use the division sign, it would look like this. The numerator, which is x plus 2 over x minus 1, and then it's divided by x minus 3, x plus 5. Well, in that last lesson we said if we have division, we can change that to multiplication of the reciprocal. So and maybe I better not write that as an x, maybe we should write that as a dot, just so it doesn't get confused with the x's. We can just change that to the reciprocal of the divisor. So we'll just flip that second fraction, and now this just becomes a very simple multiplication. So now we multiply the numerators. Well, to multiply the numerators, we have to use FOIL, right? We have two binomials, and then multiply the denominators using FOIL as well. So multiplying the numerators using FOIL and multiplying the first two, the outside two, the inside two, and the last. First two are x squared. The outside two are 5x. The inside two are 2x. The last 2 times 5 is 10. We'll go ahead and put the like terms together in a minute. The denominator, x times x, is x squared. Outside 2 minus 3 times x is negative 3x. Inside 2 minus 1x. And last 2, positive 3. Put our like terms together. We have x squared on the top plus 7x plus 10. And then x squared minus 4x plus 3. Now at this point in the problem, people always ask, well, now do we have to factor this? Do we have to factor the numerator and the denominator? Well, if we did, we would be right back to where we started from, right? We would be right back there, which is the factored form. So the answer is no. That would just be undoing what we just did. So we don't want to undo what we just did. This is our final answer. So it looked a little scary, but it wasn't any harder than what we had already done. Now, of course, we couldn't leave it at that. We would have to step up the level of difficulty a little bit. So let's take a look at example B. Well, in example B, before I can do this, change this fraction bar to division and then change it to multiplication, I have to actually simplify my numerator here. Because see, the numerator has two fractions in it as well. And we want to combine them to make a single fraction. So then I can proceed like I did in example A. So the first thing I have to do is take a look at 3 over x and x over 2 and add them together. And that means I need a common denominator. Well, the common denominator of x and 2 is 2x. So that means I'm going to have to multiply the top and the bottom of this first fraction by 2 and this second fraction by x. And that way both of them have a denominator of 2x. So that's going to make this numerator now, I have 6 over 2x plus x squared over 2x. And I can kind of just combine them together now. And if I want to just maybe rewrite it here, just erase this out, put them together with a single denominator. It's 6 plus x squared, or x squared plus 6, either way you want to write it, over 2x. So now I'm back to a fraction that looks like example A. So now I'm going to change that to division and then switch it to multiplication of the reciprocal. So do I have to show all those steps? Well, if you're comfortable with just going straight to flipping the denominator, you can do that too. So that would look like this. And I actually like to switch that around and put the leading term first. So I'm going to put x squared plus 6 over 2x. And then I'm going to change it to multiplication of the reciprocal of this denominator. So I'm going to flip that over and make it x over x minus 1 so that I can change it to multiplication. And now all I have to do is multiply. So I'm going to multiply tops and bottoms. Well, when I multiply the top, I'm multiplying this whole quantity, x squared plus 6, by x. So that makes x cubed plus 6x. But you know what? I just noticed something. So I'm going to take a step backwards, and I hope that you have an eraser that you can move a step back like I am. And I thought, I kind of didn't see this right off the bat, but then as I looked back, I noticed that there's an x on the top here and an x on the bottom that I could just go ahead and cancel out. And that's going to make things a little easier. Because then that really means that all that's left on the top is x squared plus 6. And all that's left on the bottom is 2 times x minus 1. And I could either write that as 2 times x minus 1, or I could write it as 2x minus 2. And my numerator is x squared plus 6. And that's my final answer. And we're going to go ahead and leave example C as another do in class. This gives us a really nice sampling, one adding, one subtracting without common denominators, and one simplifying complex fractions to do together when we meet again. So I'll see you then.